Let's sort out how polytropic processes work with ideal gases. So, we're given an ideal gas. I have to apologize, the drawings for this video aren't that engaging. It's a big parcel of gas. And we know for that there are 4 different versions of the ideal gas law. I'm just going to pick one. How about P big V equals mRT, where if you recall, P is the pressure, V is the total volume, M is the total mass, R is the specific gas constant for this ideal gas, and T is the temperature. And this is a polytropic process, so we know how those work. It's PV to the N equals constant. So let's combine these, and the goal here is to come up with a relationship between the temperature and either the pressure or the volume ratio. We already know the relationship between the pressure and the volume for a polytropic process, but since we have an ideal gas, we can tie in the temperature too, which of course may be useful. Temperature is a directly measurable quantity. Okay, so we'll start with the ideal gas law, PV equals mRT. And what I'm going to do is take a ratio for each of the initial and final states. So if you think about it, if PV equals mRT, it must be true that PV divided by mRT is equal to 1, and that has to be true both at the initial state and the final state. So we can say that that ratio, PV over mRT, must equal the same value for the initial case on the left, subscripted with 1, and the final case subscripted with 2 on the right-hand side of that equation. So we're setting up a ratio problem. The nice thing about this is that we're dealing with ideal gas, and it's implied to be a closed system, so we're not worried about losing mass. We're certainly not changing its composition. That means that M and R are the same on both sides. We don't need to subscript them, and so we can cancel those out. So we get that the ratio PV over T is constant for the initial and final state. Okay, let's solve for the temperature ratio. So T2 over T1 becomes P2 V2 divided by P1 V1. Okay, we'll move that up and keep that. Now we're going to use the fact that we have a polytropic process. So far that actually hasn't come up, but now we need to use it. So we know that the relationship is that PV to the N equals constant. That's true in the initial and final states as well as any point in between for a polytropic process. Well, we can rearrange this to solve for P2 over P1. So let's do that. P2 over P1 becomes the volume ratio V1 over V2 now raised to the nth power. You can convince yourself of that from the polytropic process equation. So our goal now will be to take this expression and plug it in up here so that we have temperature in terms of volume exclusively for an ideal gas polytropic process. Okay, let's do that. So we plug that in and we get that T2 over T1 is now this combination of volumes, but we're working exclusively in terms of initial and final volume and the polytropic index N. So that second part, V2 over V1, we can write as the reciprocal of V1 over V2. Normally that would be a weird choice, but the idea is to combine the arguments, so we want V1 over V2 to some power, and indeed we can rewrite that as T2 over T1 equals the quantity V1 over V2 to the N minus 1 power. Okay, so that's our first relationship between temperatures and volumes for a polytropic ideal gas process. Pretty straightforward. So if you can measure volumes, you can get temperature. Likewise, you can work backwards. If you measure the temperature ratio, you can get the volume ratio. And you don't even need numbers, you just need ratios. Let's come up with a similar expression for the pressures and temperatures. So we can start back with this, which comes directly from the polytropic process relation. So you can work out the relationship between V and P in terms of V1 over V2. And now we can just substitute this in, right? We just solved for V1 over V2. We can combine that with the top expression that we just derived and say that T2 over T1 must now be P2 over P1 quantity raised to the N minus 1 divided by N power. So if you know the polytropic index, and again you need something like initial and final pressures or initial and final volumes, you can immediately go through and get the temperature ratio for that process. That's a convenient aspect of an ideal gas.